Hello everyone watching this video. Today in this video we will discuss the angular momentum. So here previously we discussed the torque and now we have new topic, the angular momentum. So before starting it, I would like to explain something. In the linear motion we had the inertia. In the linear motion we have the inertia, but in rotational motion we have the moment of inertia. In the linear motion we had the force. In the rotational motion we have torque, which is called moment of force. So these two things we have discussed in this chapter. So these things came from the linear motion. In linear motion we studied the inertia, and now we have discussed the moment of inertia, to which the moment of inertia is the part of rotational motion and it is like the inertia in the linear motion. And we have discussed the torque in rotational motion, which is like force in linear motion, and torque have one more name which is called moment of force. So here we converted moment of inertia into moment of inertia and force into moment of force. So now we convert our momentum in the moment of linear momentum. So in the linear motion we had the momentum, and now we called the moment of linear momentum angular momentum. Angular momentum. So here we have the inertia converted into moment of inertia in rotational motion, force converted into moment of force, and the linear momentum converted into the angular momentum. So things are equally same as we discussed previously. So here this is the angular momentum is in rotational motion, which is similar as the momentum in the linear motion, and the definition of the angular momentum is the moment of linear momentum that we have discussed. The inertia become moment of inertia and force become moment of force, and which is torque. So here our linear momentum become the angular momentum due to the moment of linear momentum of a rigid body about an axis of rotation is called angular momentum. So this is a quite simple definition of angular momentum that came from its definition, its property, that it is a moment of linear momentum. So here this is the definition of angular momentum, which is the moment of linear momentum of a rigid body about an axis of rotation is called angular momentum. So here it is the definition, but the angular momentum which is derived by or denoted by capital J, and it is given as the multiple of linear momentum and perpendicular distance of it from its axis of rotation. Here in the torque we explain the torque is the R into F. These were the vector form, and we can write the force into perpendicular distance. So that was the formula for torque, and we use the same formula for the angular momentum, which is this is determined by multiple of perpendicular distance and the linear momentum. And when you write it, you can write in this form Rp sine theta, or you can say P R sine theta, and you can write in the vector form as R vector into P vector. So these three are the formulas for linear momentum. This is from definition that this is determined by the multiple of linear momentum and perpendicular distance. And what is this distance mean, we will discuss here. And when we write it in the formula of torque, we wrote that this is r sin theta into f. So here we have r sin theta into p, and we can write it in the vector form. In the here we have the sin theta, so we use the symbol of cross product between r and p. So it is very simple. Here we have a rigid body and there is an axis of rotation about it. It is rotating with angular speed omega. Angular speed omega, and here this is the center, and here we applied a linear momentum, or linear momentum at this point is p at any instant, and the distance between p and this axis is small r, and the angle between p and r vector is theta. Then we take this distance or perpendicular distance, which is r sin theta, So we don't take the distance between p vector and r and the axis. We take the distance, the perpendicular distance between the line of linear momentum or line of action of linear momentum and the center. So here we draw the perpendicular on the line of linear momentum from the center, and we take that distance, which is r sin theta. So these are the formulas. Now we derive that we know that value of p is mass into velocity. We have the value of p, which is mass of velocity. When we put it, we get the j equals to, in this formula we can say mvr, and when we put, we can write the angular momentum. We know that v equals to r omega. So when we put the value of v, j become m omega into r square. When we put the value of v, it become m omega into r square. So there are two more formulas for angular momentum. So there are basically three formulas. So this is the basic formula: perpendicular distance into linear momentum, and perpendicular distance we can write in the r sin theta form, and j in the vector form, the r vector into p vector. And here when we put the value of p equals to mv, j become mvr. This is the angular momentum. And when we put v equals to r omega, then j become m omega r square, m r square omega, whatever be. So these are the formulas for angular momentum. Now we will write the relation between angular momentum and torque. So please make the notes of it. I am cleaning it. You can pause the video and make the notes. So now our next heading, the relation between angular momentum and torque. So this is our new heading. Now we write the relation between angular momentum and torque. So we have the angular momentum J equals to R into P. J equals to R into P. So here we differentiate it with respect to time. So it will become dj by dt. So when we differentiate the angular momentum J with respect to t, we write in this form dj by dt equals to, here we have the R and P. So we write d R into P upon dt. So this R is the radius, or radius of gyration, we can say it. So it is the constant, it will come out, dj by dt become, R is constant, or it's dp by dt. So dp by dt is the rate of change of momentum, which is equals to force. or you can write also in this form that dp, you can say mv into dt, and m is constant, dv by dt, and m is constant here, dv by dt is rate of change of velocity is acceleration, and mass into acceleration is force. So there are two ways. Anyway, you can write in this form. So dp by dt will become r is constant here, dp by dt become force, dt by dt become force, and r into f, you know very well what the mean of r into f. So this is the formula of torque, which is r into f. Everyone knows that. So this is become torque become dj by dt. So in the linear momentum, in the linear motion, we have rate of change of momentum is equals to force, and in the rotational motion, the rate of change of angular momentum, is equal to the moment of force or torque. So here the P and J have the same relation, and F and tau have the same relation that I have explained in the beginning of this video. So here we write this thing in the language, the torque is equal to rate of change of angular so the torque is equal to rate of change of angular momentum. So here we wind up our today's video, and for the next video please make the notes and revise your things. Best of luck.